Professor, you're muted.
Sorry, thank you. Well, so welcome to Issues in Environmental Science for the 17th of September. We're continuing our introduction to energies and ecosystems within the planet Earth. And what we'll be doing today is continuing some of that discussion. I'll be talking about examples of the Earth system, the way in which the input of energy into the Earth system and the division of material properties within Earth creates a series of biomes, areas in which ecosystems can occur. We'll be looking at some of the principal characteristics of ecosystems. And then in your breakout session, I'm going to ask each team to choose an ecosystem and conduct some preliminary research on that, and then answer a series of questions about these ecosystems that you choose. And then we'll come back in the main session and the teams will present and discuss that. Before I begin, however, I'd like Carrie O'Reilly. Carrie, you're on the session here. I'd like you to go ahead and talk about, so Carrie and I, as I talked about Tuesday, we'll be conferring with each of the teams to really help you solidify and focus the questions that you're asking and the topics that you're going to address in your semester project. And so that'll give each of us a chance to visit with the teams, help you with research directions, and sort of get you off to a good start generally. And we're also going to take the function of trying to encourage you to be rigorous and to drill down, both in terms of the kind of questions that you're asking and the places that you're looking for resources, the research areas that you're looking into. And so, Carrie, you set up a series of appointments, and could you share your screen and show how that's going and make sure everybody's on the same page about how to set up their session?
Yeah, so I set up an appointment group in our class's calendar on Canvas, and this is the link that I sent out with that announcement on how to go about signing up for that. If you click on your calendar in Canvas, and if your this class is active, you should be able to click on Find Appointments up at the top. And then the drop-down menu, you'll have to choose our class, and then you'll be able to go through and reserve one of the appointments I've made. So
can everybody, let me ask a question of the group. Can everybody see the calendar in the homepage, in the Canvas page?
Yes.
Yes, sir.
Yes.
Okay, great. So
yeah.
you see that. Good.
And as far as I know, they should be able to see every single one of these appointments that I've put in there. There are only 15 groups and many more appointments in morning and afternoon, so there shouldn't be any issues in signing up for one of those.
Okay, so
you should be able to go in and hover over the appointment and see if someone signed up or not.
great. And so everybody will go ahead and sign in, and I think I'd like you to finalize that for next week, so we kind of know what we're facing. Everybody's got a lot to do, and we all have multiple Zoom obligations. So please go ahead and get signed up early, so we can anticipate and clear out some of these areas where we won't need appointment slots. Any questions about scheduling these team appointments?
So it's only one person, right?
Yeah, one person per team can sign up.
Can sign up.
And then whoever you're meeting with will send you a Zoom link before your meeting.
So at that time, do we all have to go, or does it just be one of us explaining?
No,
It should be all of you.
yes.
Okay.
Yes, please, as many, all of the team should be present for that, unless, somebody has an urgent excuse why they can't be there. That way we get to meet everybody, and everybody gets a chance to ask Carrie or me how to proceed.
We just go to the calendar from the main Canvas dashboard? Like it's not in the class somewhere?
You should just be able to click on that calendar icon and all those
Okay.
meetings should be there.
Okay.
Yeah, if you have any questions, you can email me or Carrie, and we'll talk you through it. But it should be pretty self-explanatory. And please go ahead and confer with yourselves. And you can talk about this when we do our breakout sessions today to make sure everybody's on the same page about when we're going to meet. Okay. Further questions about this? Okay, well, let's get started. The team exercise will go a little bit longer, and so I'll try to keep my remarks brief. I'm going to go ahead and share my screen. Okay, so as I said, we'll be talking about Earth systems and ecosystems, productivity, net and gross productivity. And then in the breakout session, each team will choose an ecosystem, some ecosystem that occurs somewhere on the planet, a forest ecosystem, a rainforest, a desert, whatever it is. Pick that out and then answer the questions that are outlined in the exercise as it's stated in the Canvas session, so everybody should be able to get at that. And so we'll try to leave as much time as possible for this, because this is going to take you a little time, because you are going to need to do some research, pull in some sources from the web while you're in your exercise. Okay, so we talked on Tuesday about trophic level efficiency. And I gave the example of a consumer and a producer, and I talked about my production of reading book stands, and I pointed out that if I were this is an example, it's sort of a human example, and I'm saying that if I were an organism producing book stands from lumber, my efficiency would have been about 13% efficiency. So that sort of consideration can apply to all trophic interactions, to all exchange of matter by consumption or production. So no matter how efficiently living things use energy, there's a ratio of output to input. So no system is 100% efficient, because energy is usually degraded or lost as it goes from one trophic level or another. And typically that loss, when one organism consumes another organism, is about 90%. Only 10% of that of the energy is retained. So there are examples, farming corn. How much energy do we have to put in to produce sugar? Transportation, how much energy does it require to produce movement? And organisms and ecosystems differ greatly in how efficiently they're able to use matter and energy. And this loss of energy, loss of matter at each level, each trophic transfer gives rise to this concept of pyramids of different types of organisms. And so primary producers are at the base of the food chain. They're the ones that produce the organic material that's then consumed, moving up in the food chain. Primary consumers eat the primary producers. Secondary consumers eat them, and so forth. And there's a loss at each level. And so a simple ecosystem here might be the Arctic ecosystem. The Arctic ecosystem is an example of a simple ecosystem because there are relatively few components. I mean, it's a source, it's a habitat in which the energy and availability of resources is constrained by temperature, by seasons, and so forth. And so in the Arctic ecosystem, the primary producers are phytoplankton, plant plankton living in the ocean. The next level would be herbivorous zooplankton, followed by carnivorous zooplankton, followed by fish. Arctic char is a type of fish. The char are eaten by capelin. And so, at each of these levels, there are other components that are consuming these. So Arctic cod are eating zooplankton and carnivorous plankton. Seals and different types of seals are eating the larger fish, and then these organisms are food products of other components in here. So just looking at these ecosystems, you would say that the largest biomass would probably be the plankton, followed by decreasing at each level. And then when you get up to the upper levels, the polar bears, the orcas, the killer whales, these are going to be the smallest levels in the system. So we can classify this in terms of productivity. The gross primary productivity is the total amount of energy that plants capture and assimilate over time. So if you think about the energy that's driving plant production, that's energy coming from the sun, combined with available nutrients and other limiting factors, water, soil types. And that goes to that total productivity represents the total amount of energy that plants capture and assimilate for any time period. But there is a cost to that. And that cost is often referred to as respiration. That's the cost of being a plant, of respiring water, of transferring energy in different chemical types. And so the net primary productivity is the amount of plant material which is added either to the individual plant or, in the case of a forest, to the overall forest. And so the productivity after net productivity is the production after the losses of respiration are subtracted. And that energy, the net primary productivity, is the energy that's available for the next level in the organism. So in my example of building book stands, I start with the lumber, and I put in effort, I use energy, and then I produce a much smaller amount of net production. Okay, so we can use this concept of productivity both to characterize the losses that occur at each stage, and then to characterize the way in which these sort of systems produce characteristic food pyramids and food webs. And so here's an equation that spells this out. So net primary productivity is equal to gross primary productivity minus the respiration costs. And so in the case of plants, this is cellular respiration. Okay. So when we start organizing these different groups, the primary producers, secondary producers, and so forth, into systems, we start talking about ecosystems. And here are some key concepts for ecosystems. There's an energy flow through the Earth system. Producers, consumers, decomposers. There are non-living and living components. Nutrients, which are chemicals necessary for life, are cycling through different biogeochemical pathways within ecosystems. Ecosystems are organized according to species, to communities, to different groupings known as biotomes. This organization produces a sort of trophic pyramid that I've discussed. And then there are individual components of the ecosystem that play key roles. So if we think of a forest ecosystem, we can think of the key role played by the trees in a forest ecosystem, in providing the major biomass, providing habitat for many organisms, and providing the basic primary production that supports higher level trophic interaction. But within that ecosystem, there are species that perform critical functions that allow the ecosystem to retain its stability. So a classic example of a keystone species is the sea otter. And a sea otter, everybody knows what a sea otter is. It's a cute, fuzzy animal. And sea otters live on the Pacific coast. They eat various invertebrates that live on the bottom of the ocean. the examples are sea urchins. They also eat abalone, other shellfish. Well, it turns out that the major, biomass component of the ecosystem in which sea otters are found are kelp. Kelp are marine plants that attach to the bottom. They provide primary production and habitat shaping characteristics for the kelp ecosystem. And sea urchins will attack the base of the kelp, and if unchecked, they could wipe out a kelp forest. Well, sea otters are a keystone species because they prey on the sea urchins, and so they stop the sea urchins from wiping out the kelp. And so in the early part of the 20th century, late 18th century, sea otters were hunted for their fur, and they were just about extirpated in the Pacific coast. When that happened, the sea urchins overtook, and kelp forests really declined in area. So keystone species can be absolutely critical in maintaining an ecosystem. There are also ecosystem engineers, and a classic example of an ecosystem engineer would be the beaver. So beaver are affecting watersheds. They cut down trees, which they eat the leaves in the trees, and they also use the trees to dam up rivers and waterways, creating areas that are flooded. And these flooded areas, these flooded waterways provide the beaver with habitat, and they protect it from predators and provide other functions. Well, the tendency of beavers to produce these ponds and water areas within their ecosystem has a great effect on the availability of habitat and nutrients for other organisms. So ecosystem engineers, keystone species, these are critical roles played by individual components of an ecosystem. They may not be the biomass dominant, but they have nonetheless very important roles. Another component of ecosystems are invasive species or invaders, and these are organisms that are introduced often by human action into ecosystems, and because they tend not to have natural predators within an ecosystem, they can sometimes, their populations can explode to the detriment of the ecosystem. And one of the great examples here in Florida is the Burmese python. Burmese pythons, of course, are not native to Florida, but they were introduced as a result of careless pet owners. And I guess there was a reptile farm that was flooded during Hurricane Andrew, and many Burmese pythons escaped into the Everglades, where they don't have natural predators, but they are very efficient predators themselves. And so there's a great deal of concern that the Burmese python is altering the characteristics of the Florida Everglades and elsewhere by consuming organisms, everything from rabbits to raccoons, and even deer, and in some cases alligators are eaten by these voracious predators. And the removal of these natural components of the system alters the ecosystem. So invaders can really change the characteristics of the ecosystem in unpredictable ways. Of course, it sort of depends when the invasion happens, because in history, there have been many sort of introductions that have altered the characteristics of the ecosystem in fundamental ways. But then subsequently, after some period of time, the ecosystem readjusts. And so if we think about the ecosystem that was encountered in North America when European settlers arrived, there were a number of species which we would consider keystone species that were introduced, that were essentially invasive species. And it might surprise you to know, for example, that prior to the arrival of Europeans, there were no earthworms. in the North American continent. So earthworms were introduced by soil that was carried over from Europe, and earthworms were, have had an open niche, and they began expanding, and they altered the characteristic of soil. So we don't think about that anymore because that happened a long time ago. Another example of an invader are honeybees. Honeybees are not native to North America. They were introduced by Europeans, but they have, in many cases, displaced native pollinators, and many ecosystems, particularly agricultural ecosystems, depend on these introduced forms of pollinators, and so there's been a shift in the ecosystem.
They find out, sorry, how did anyone find out there was no earthworm?
Well, they can look back in soil samples. There are samples that are preserved, fossilized records, and it was also known that they can classify earthworms in terms of their genetic origin, and so they can confirm that the earthworms that are found here were originally native to Europe.
Oh, okay.
Okay, so that, it's a sort of a surprising fact, and we think of earthworms as being this healthful component of the system, and indeed they are. We have healthy forests and healthy soils and so forth, but that represents a different type of ecosystem than was here originally, and so sometimes it's very difficult to appreciate these changes. Okay, and then all ecosystems have dynamics. They change over time. And some of the changes are seasonal, with warming and cooling, or wet seasons and dry seasons. Some dynamics of some changes are a result of sort of decadal changes that occur over a sort of a 10-year period or even longer periods. And these changes can be sort of oscillatory. They can go back and forth, or in many cases, there can be sort of a shift in the dynamics of an ecosystem that produce permanent change within ecosystems. And that may be something that we're looking at, unfortunately, in the changes that are occurring in the West Coast due to climate change. And so the Western United States is adapted to having large areas of forest cover. This forest cover are adapted to relatively cold winters, certainly at higher altitudes, and a characteristic amount of rainfall. Well, if the temperatures change and the amount of rainfall changes, then that ecosystem may no longer be stable. So we may unfortunately be looking at an ecosystem altering level of change that's occurring because of the hotter, drier conditions that seem to be prevailing over the last 10, 15, 20 years within the West Coast. And so, these dynamics may be cyclical, or they may be permanent changes. So these are some key concepts of ecosystems. Well, let's back up a little bit and think about the Earth ecosystem. So we've talked about inputs and outputs, and we can classify ecosystems as being closed or open. Well, within the Earth, all of the ecosystems are somehow connected one to another, but those connections may be open and large, or relatively constricted. Over short time scales, the Earth is an open system for energy. So energy is continuously arriving at the Earth from the sun. That energy flows through the Earth ecosystem, performs myriad tasks, moves the atmospheric forces around, causes circulation in the ocean, of course produces primary production, and that energy is dissipated, changed from concentrated light energy into less concentrated heat energy, and then re-radiated into space. So Earth is an open system for energy. It's a relatively closed system for matter. The rocks are being recycled through plate tectonics. Water is being recycled through the hydrologic cycle. Precipitation, transpiration, return flow. Organic matter is being cycled through the food chain. So everything is moving around within Earth systems, but almost no new material is arriving, and almost no material is leaving. So it's, relatively speaking, a closed system, certainly over shorter time spans. If we look at very, very long time spans, the Earth may be somewhat open to matter. Comets and meteors can arrive, and some matter is, certainly there's going to be a loss of gaseous material into space. When Earth was a young planet and forming, the arrival of material, of course, Earth formed from the coalition of rocky material circulating the proto-sun. And so at that time, the Earth system was relatively open. Things were colliding and collapsing. But right now, we find ourselves in a period, billions of years in length, in which Earth is, relatively speaking, a closed system. Well, for human populations, are Earth systems open or closed, do you think? That we have food production and essential nutrients have to happen. So we have to support our human population, and this requires nutrients. And we're going to be talking a lot about essential nutrients and nutrient cycling when we get to the next chapter in the book. So I'm going to hold off on that discussion. But I'll just point out that there are cycles of matter moving through the system. These are somewhat fuzzy definitions, so we can think about the hydrologic cycle. First of all, we'll define a cycle as an exchange of matter among separate components. So, and matter or energy moves from one component to another in terms of flux. So flux is defined as a transfer of matter and energy over time. And so two systems that are linked in a cycle, A and B, there's a flux. So this is an open system. It's at equilibrium. So there's a flux from B to A and a flux from A to B, and these are equal. Both systems retain themselves relative size. The hydrologic cycle, which is the largest and most complete matter cycle on the planet, involves almost all of the components of the Earth. So there's bodies of water, lakes and oceans. The water is evaporating into the atmosphere, so there's one cycle. There's a precipitation flux from the atmosphere to the land and water. There's runoff, and so there's this exchange of water moving amongst these different cycles. There are also earth cycling of chemicals, and we'll talk a lot about the different types of chemicals. The major components, the major essential nutrients on Earth are oxygen, hydrogen, carbon, nitrogen, sulfur, and phosphorus. These are the big six Earth nutrients, and they're moving a lot of times with the hydrologic cycle among the different components of the Earth system. So the carbon cycle, for example, there's a biological uptake of carbon from the atmosphere. Some of that carbon is mineralized when some of the carbon is cycled into the ecosystem by consumption and the trophic pathways. Some of that carbon ends up mineralized when plants die and can be buried in the rocks. And then some of that can be returned to the atmosphere over time. So these cycles, these components are linked by these different processes. Any questions here about cycling and what I've covered so far? Okay, well, let's talk a little bit about this first concept of energy flow into the Earth system. And we're going to focus on solar energy arriving, because that's the energy which drives most of the biological productivity on the planet. And there's a key feature to the way in which solar energy arrives at the Earth. So the sun is putting out vast amounts of solar energy, and a teeny tiny fraction of that, hits our little blip of a planet. But effectively speaking, this energy is traveling in straight lines from the sun, and it's arriving at a spherical body. Well, if you think about how light energy or energy hits a inclined surface, if the density of that energy is constant, but the surface is either relatively perpendicular to the incoming energy or at an angle to the incoming energy, the greatest concentration of energy is going to be where the Earth's surface is, relatively speaking, perpendicular at right angles to the incoming solar energy. And where would that be on Earth? Well, that would be at the low latitudes, the equatorial region. As you go further up or further down into the higher latitudes, of course, the curvature of the Earth means that the relative inclination of the Earth's surface increases, and the same concentration of energy is spread out over a larger area. This is, I'm sure you've heard this kind of concept before. Well, what this produces are differences in the average amount of solar energy available at different parts of the Earth's surface. So, let's look at this figure here. You can ignore this text. And so what we're looking at here is latitude. This is the equator, and this would be the North and the South Pole. And over here is time. And so this is from March 21 to March 21, the equinox. And so this is a complete solar year for the Earth. And what you'll see is that the hottest temperature on average is at the equatorial area. It's actually displaced slightly north because of the arrangement of continents. And during the summer months, northern summer months, the temperature rises in the higher latitudes and is much colder in the lower latitudes, and that's due to the relative tilt of the Earth. And then, as we proceed from the summer months in the northern hemisphere to the summer months in the southern hemisphere, the pattern is reversed, and so we get this seasonal shift in temperature across the planet, and it's controlled by the latitude by latitude. So, if we look at, how this plays out on Earth, we can see that some of the, so this is a composite image, and the green color is an indication of primary production by plants. And so what do you see when you look at this? You see areas of high productivity marked by green. And you can see very high productivity in certain areas, the equatorial South America, this is the Amazon basin, and then equatorial Africa. These are areas of high productivity, high plant biomass, and consistent seasonal input of temperature. We also see very relatively high productivity in temperate areas of North America and Europe. You can also see that there are bands of relative aridity, of relative low production in the temperate regions, both in certainly it's pronounced in Africa. You can see the Saharan Desert, and then the Namibian Desert of southern Africa. You can also see desert areas in Australia. And so these are areas where, although there's a lot of energy from the sun, there's relatively little rainfall. And so that produces desert areas. You can also observe that the green isn't just limited to the land areas. There are levels of high productivity in the ocean, and you can see that this high productivity are in the temperate regions of the ocean, both in the northern hemisphere, and then there's very high levels of ocean productivity in the southern ocean, in the southern hemisphere. And so, these seasonal patterns and this latitudinal distribution of energy, together with patterns of rainfall and atmospheric circulation, which we'll talk about in subsequent chapters, produces this sort of characteristic distribution of productivity across the planet. I'll point out something else here. Overall, terrestrial ecosystems contribute about 2/3 of the global net primary productivity, and the marine ecosystems contribute about 1/3. But if we look at that in terms of, if we look at primary productivity as a source of our oxygen, that's saying that about 2/3 of the net primary productivity would come from land and 1/3 from the oceans. Well, there's about twice as much or 3 times as much ocean area on the planet as there is land area on the planet. So although the net primary productivity from terrestrial ecosystems is higher per unit area, because there's such a larger area of ocean, the two of them are about equivalent in terms of oxygen production and global primary production. Okay, let's see. So this combination of different energy inputs and different rainfall inputs produces a characteristic division of the planet into biomes. And so these are terrestrial biomes. Biomes are large regions with similar amounts of temperature and precipitation. So temperature and precipitation define the possibility, the non-living possibility for supporting life. And so here we see a diagrammatic representation of the major biomes of Earth. And you can sort of compare that with the picture that we showed earlier of the satellite image of productivity. So this equatorial region of South America and Africa, these are tropical rainforests. And then there are temperate forests across Europe and the United States. The boreal forest, which is characteristic of Canada, Russia, and then portions of South America as well. This is also a region of very, very high standing stock biomass. So these are the characteristic biomes on the planet. The ocean is also zonated, but the factors that are driving zonations in the ocean are quite different from those which are defining terrestrial biomes. The zones of a marine ecosystem are defined by how much light is available for primary production within the ocean. So light is extinguished as it moves through the ocean, and so within the upper when you get below about 200 meters depth, there's not enough light energy to produce, to support primary production. So most or all of the primary production in the ocean is taking place in the surface. So that the relative surface area, or the relative depth, is one defining factor for ocean biomes. Another is proximity to the shore. And other production, so the proximity to the shore is one of the things that controls the availability of nutrients that are coming off of the terrestrial ecosystem. So the terrestrial biomes are zoned by characteristic temperature and rainfall. The ocean biomes are zoned by available light and proximity to land and availability of nutrients. And we'll talk more about this as we continue with the course. Okay, so that's a very short overview of global ecosystems. I'll talk a little bit more about different characteristics of ocean systems. But one of the points that I really wanted to emphasize is that the Earth that we're seeing today has been totally modified, completely altered by the evolution and development of life forms. So life began appearing on Earth about 3 billion years ago, and originally there was no oxygen in the Earth's atmosphere, and when green plants evolved, they altered the atmosphere totally by releasing oxygen from CO2. So the plants use carbon for their biomass, and oxygen is a waste product. The leftover oxygen totally altered, totally changed the original Earth atmosphere, and gave rise to other forms of evolution. And so about 5 or 6, 650 million years, I guess, was the beginning of the Cambrian explosion of life. So multicellular life. So the early life on the planet was all single-celled organisms, bacteria, and eventually green algae. About 500 to 600 billion years ago, larger multicellular life forms began to evolve and develop. And the development of metazoan life has also totally transformed the Earth ecosystem. And we'll also talk more about that later on in the course. The other great factor that I want to introduce is the way in which human life has altered the planet. And this is something that we'll come back to again and again, and indeed you'll be looking at in your exercise today. So the Industrial Revolution, was a great boon in many ways for human population. So with the development of harnessing energy, human populations, human civilizations were able to have specialized workers. They could produce surpluses, and also they began to alter the quality of the water and the air, so there were problems with pollution, problems with water supply, and so forth. And then most recently, we're seeing the effects of the way in which our use of fossil fuels has increased the load of carbon dioxide in the atmosphere and begun to alter the planet. Other factors in the development of human impact on the ocean are the development of agriculture. So human populations were limited at various times in human history by the availability of foodstuff. And so the invention of agriculture as an alternative to hunting and gathering allowed the human population to increase in size. The development of the Industrial Revolution allowed another increase in size. But at each of these steps in human evolution, people would sort of outgrow their food supplies. And at various times, human populations have been limited by the availability of food. One of the big changes in the 1970s and 80s was the Green Revolution. And so this was the development and the widespread use of specialty agricultural crops, wheat, corn, rice. And these crops had been bred to make use of artificial fertilizers and modern agricultural techniques. And so the Green Revolution allowed the human population to triple. So when I was born, the population of the planet was about 2.2 billion. The population of the planet now is about 7.5 billion human beings. So in my lifetime, we've seen almost a tripling, or indeed a tripling of the human population. And much of that was due to changes in agriculture. But this large population then puts incredible pressure on the overall Earth ecosystem. Fossil fuel dependency, our the current population of human beings on the planet could not exist in our present configuration unless we had available fossil fuels. And so we are, in many ways, dependent for our food supply. We are eating oil or eating fossil fuels because fossil fuels make possible the green revolution, the modern agricultural practices. And so fossil fuel dependency has also, increased our population, but it's also yielded excess CO2 and forced atmospheric warming. So life has changed our planet both at the inception of life and evolution, different stages in evolution, and then more recently, we, the kind of life that human life has evolved into has also begun to alter the planet in, profound ways. So we're going to break into our groups here, but we want to look at variation of net primary productivity by ecosystems. And this is just by way of saying that we can have different levels of primary production in different productivity, net productivity in different ecosystems. And so, you can see a graph here comparing the productivity of different types of ecosystems. And you can see that algal beds and reefs, tropical forests, swamps, marshes, and so forth are very productive ecosystems at one end of the scale, and you get into open ocean, desert and semi-desert, extreme desert, rock, ice, and so forth, very limited net primary production. So the ecosystems differ in those ways. Okay, well, that was as much as I was going to say about ecosystems. These slides are available to you in the PowerPoint, which is in the module for this week. So these slides that I've just been showing to you are available in the module if you would like to refer to them. But now we're going to break into our groups, and you're going to conduct this group exercise. So, Carrie, I'm going to assign you to only clams. Carolina Garcia, where do you?
Planeteers.
Planeteers. We got to figure out a way to get you in automatically.
Yeah.
Darren, you are in Planeteers too, right?
Aquatic junkies.
Oh man, I'm gonna get this someday. All right. And Whitney, I've done this before. You're in
Green machine.
Green Machine. Emily, where do you go? Emily? Emily Cabrera, are you muted? I don't ever get to hear from Emily. All right, Kate, where do you want to be?
Team title.
Team title, okay. Emily Cabrera, can you please check in? Emily? Hi. Do you need to be somewhere?
Yeah, I got up to use the restroom and I guess I completely missed my join breakout room. And I'm pushing the function at the bottom and it's not putting me in.
You should be in Aquanauts, right? I think you should be able to, it's not letting you in?
No, when I push the join breakout room, it's not doing anything.
Huh.
Sorry, I got up to use the restroom real quick and I missed the function that pops up when you first start it.
Okay. Let's see, what am I gonna do? How am I gonna, why don't you leave, can you leave your breakout room?
No. I could leave this and then try to come back in, but I don't know if that would do anything.
Because it shows you as being in the room, but it shows you as not joined. Let me just check something. I'm going to try moving you into another group. I'm going to move you into Beach Please, and you can apologize to them. Let's see if that works.
Okay, and then move me back into Aquanauts or stay in Beach, please.
And I'll move you back into Aquanauts.
Okay, all right. Thank you. Sorry.
Okay, so now I moved you back into Aquanauts. Can you join? What message do you get when you try?
No message is popping up.
Are you registered? What are you?
Yeah, so when we first had the problem and I was like going through a different link, I started going through the link that you had suggested and I haven't had a problem since, but
Were you able to join last Tuesday?
yeah, I've been able to join every time since that first time we had a problem, but I really think it's just because I missed the initial, like you putting the button up to join.
Yeah, I don't seem to be able to do anything about it, Laura. Maybe you could try logging off and logging back on.
Okay.
Quitting out of Zoom and coming back into it.
Okay.
Because I'm not able to get you in there.
All right. Let me try that.
I just wanted to tell you that your teammate Laura is having trouble getting in. I've been trying to push her into the room and it doesn't seem to work. Are you guys finding an ecosystem that you're able to see all the questions?
Yep, we did a Word document. So she's able to access the Word document. So we're all working together. We chose the Springs ecosystem. So we're working on that together. She just isn't in the video, but we have her in GroupMe and we have her on the Word document.
Okay, okay, good. Well, I'll see if I can get her in. All right.
All right.
Okay.
Sure.
Bye.
Anybody here?
Hello.
I don't see. So you have, you got your video turned off then.
Yeah, I mean,
We're all talking.
You're all talking. Okay.
yes.
Yeah.
All right. So however you work it out. So what are you using for to work on it? You sharing a document?
Mm-hmm.
Yeah, we've been using the collaboration, the Google Doc.
Okay, perfect. All right then. I just want to just check in, going from room to room.
Sounds good.
Taylor, are you?
Yeah, sorry, I just showed up to class. I was late this morning.
Okay. What's your group?
Beach, please. I think we're group 1.
And you're Aquanauts, right, Laura?
Yes, I am.
Let's try one more time.
Thank you. Perfect. Thank you so much.
Hello, Ferns. I'm just checking in. How's everything? Defining what ecosystem have you chosen?
We chose the rainforest, specifically the Congo rainforest.
Congo rainforest. Cool. All right. And you understand all the questions, how to answer those questions and how to go forward?
I had a quick question.
Sure.
Because the Congo Basin rainforest is like its own biome. So would I just consider, like for the first question where it says in what biome, would it just be a rainforest biome?
Yeah, rainforest biome. And exactly.
Okay.
Yeah, that's a little overlapping there because it, defines.
Yeah.
But, okay.
Yeah. Thank you.
All right. So, hello.
Hello, sir.
Aquatic junkies, how you doing? What ecosystem have you chosen?
Tropical rainforest.
Tropical rainforest. That's a popular one.
A couple of them has done it.
Which tropics?
We're actually basically going across the board. I'm defining that they're based between latitudes 23.5 north and south, the Tropic of Cancer and Tropic of Capricorn, and that they're found Central and South America, Western and Central Africa, Western India, Southeast Asia, New Guinea, and in Australia, and that they're mostly defined by the amount of rain they receive must be at least 1,750 to 2,000 milliliters of rain per year, distributed relatively evenly.
Okay, well, why don't you, while you're doing that, why don't you think a little bit about the soil types in tropical rainforests, because those are very distinctive, and that's something you ought to look at. How do the soil types in tropical rainforests differ from the soil types in temperate rainforests? So I'll pose that question for you. All right, I'm going to leave.
Okay.
Carrie, are you, where are you? There you are, okay. So everybody doing okay here? Can't.
We are. We're
Okay.
we're over in a Zoom document working together.
Okay.
Or I am.
Good enough.
Google
Good enough.
Drive.
All right, I'm just checking in. You have any questions about what ecosystem did you choose?
Freshwater. Yeah.
Yeah.
Freshwater ecosystem. Okay. Well, can you be a little more specific? Because there's fresh water in a lot of different places.
Well, from what I saw, I think it's mostly like marshes in like the Everglades.
Okay. So you're taking a marsh ecosystem in temperate, semi-tropical regions, right?
I wrote a whole paper on this last semester.
Yeah, go ahead.
And if anyone has any sources, Carrie took points off last time for because we didn't like specifically cite anything. So.
Ah.
Oh wow, I didn't know that's how it was.
Yeah, I
I
saw
don't-
that.
Well, we
Good
usually
practice.
we usually get everything done during class, and I think everybody else maybe doesn't, and they just turn in something better later.
Okay, looks like all the rooms are closed. And I guess what I'd like to do, I think you're all going to be turning this in and everything's working. What I'd like to do is just have a quick check-in on how this is going for you, because this is a new way of organizing classes, doing these breakout rooms, inverting the classroom where you do a lot of your studying on your own, answering the questions, reading the chapter, and so forth. So I'd like to just have a quick poll about how that's working so I can get a sense of, if I need to change anything fundamentally or if we can just sort of tweak around the edges. So I'm going to launch a poll here, which is anonymous. And please go ahead and give me your response to this poll. Let's see. Access. Let's check in. So I'm going to ask you here, how is the inverted classroom and the team exercises? So the way that we've been running the class, where I give a brief lecture about components of the chapter, but don't try to cover everything in the chapter. And then you break into team, breakout rooms and work together with your team. How's that going for you? And do I need to have a major course correction? I guess is what I'm trying to find out. So looks like okay, go ahead and finish your answer, and I'll go ahead and end the polling. All right, so it looks like excellent. I'm learning a lot, and mostly good is where most everybody is, and I think that's as good as can be expected here. I think rather than go around and ask the different teams to talk about their ecosystems, we'll grade that when we look at the assignments. But I'd like to open the floor if there's any suggestions for ways that we can improve this, or any ideas or things that aren't working for you. Please feel free to make some comments here. We got about 5 minutes left. Any thoughts? Aaron, did you want to comment?
I think that there should almost be like a lecture that we can go to online at a later time on our own time. That's a little bit more in depth, and then focus more on our time here in our groups. Because I think it's more difficult for us to get together in our groups in different times than it would be to do our group session during this class period, and then be able to go and on our own time listen to your lectures. That would just be a suggestion.
Okay, so you'd like me to record a lecture.
And then be able to watch that at my own leisure, and instead of having just, 20, 30 minutes of because I think your lectures are interesting, but I think they're cut short because you're always trying to get into these groups. If we can, maybe do a solid hour of group time and then listen to your lecture at our own time. I don't know. That's just my opinion. I don't know how anybody else thinks about it.
I can certainly do that. I find that when I'm trying to give a lecture without any feedback, I find it really difficult. But I can work on that and I consider it. Now the PowerPoints, are there for you to look at, and maybe I can try to record more material on the PowerPoints to try to enrich those a little bit.
Yeah, I'm more of an old school face-to-face kind of learn guy, like sitting in the classroom. So this whole thing is new to me anyway. But I enjoy the lecture part of all of my classes, and I just wish there would be more of it.
Okay, well, I think I had a problem recording the lecture last time, but the lectures are uploaded to that YouTube channel. You can always go there and see look at this material over. All right, any other comments? Any other comments? Yes, Hannah.
Yeah, I was just gonna say I have one class where like we do something similar where like you lecture and then we do something with a group at the end of the class period. And in the PowerPoint that the professor posts in Canvas, there's like a space to put notes on the bottom of it, and she types in notes that were like key things that she might have said that aren't like stated anywhere on the slides, just so that you can like look through the slides and have a little bit more information at once than if you're just looking at like what's posted directly on each slide.
Okay, yeah, I have that a lot. I could try to open that up for you a little bit. Okay. All right, well, I'm trying to make this a good experience, and it's a different way of teaching, and I think the teamwork in particular, that really is an emphasis of this class, and I hope that works for everybody. So far, it seems like there were pretty minimal problems with the teams, at least in terms of that poll. So hopefully that'll continue going. And then I'll be, Carrie and I, one advantage to having this, this system is that you will get sort of more, tutoring time when we do our individual conferences, and we'll do conferences for, every one of the milestones. Carrie or I will meet with every group to go over your milestone assignments and make sure you're on track. And that should also have the effect of improving your grade as well. Okay. All right. Well, we've come to the end of our period. It seems like I could use more time in these lectures. It does seem to rush a little bit. If we had, it seems like if we had 2 hours, that'd be a longer period. But I think we could have more, discuss these things and have a little bit more time to flesh things out. But we're stuck with 1 hour and 15 minutes, and we'll make the best of it. Okay, let's see. All right, so thanks everybody. I will, and I appreciate the feedback that I'm seeing in the chat here as well. Okay, so everything will be on the board there, and I will see you, we'll be seeing you next week to go over your milestone 1. And then, of course, you have the team homework assignment and the quiz for the next chapter in the Hasselzall textbook. All right, bye everybody. See you. Oh, have a good weekend.
Professor, I just want to say, in my opinion, I like the fact that we have group and lecture. I just feel like when we do our group or like the side group things, it doesn't, like, it's too short almost. So by the time we get settled and figure out what we're going to be doing, we're like halfway through it.
Yeah.
So we don't get to collaborate on the whole thing. And I think that's the most useful part of it, is like talking between each other, trying to figure it out.
Well, hopefully, the idea of, having a concentrated time there, it gives you a chance, and you might have to come back afterwards and, you know, and sort of finish off the assignment. So,
All right.
okay.
Thank you.
Did you have a comment, Laura?
Yeah, something that's been helping my group is at the beginning of the lecture, we'll have the Google Doc running so that we automatically like see the questions, you know, so just getting a jump start on that really helps my group. And we have like a group chat as well.
I agree with what Laura just said. That's what my group has been doing as well. And it does give us plenty of time to work on the questions once the group time starts.
Okay, all right.
We do
Yeah,
the
so
same.
that's a little heads up for everybody is to get the Google Doc open with the assignment, because that's always posted ahead of time. And then, like you say, you're not sort of trying to organize yourselves. You already know right where you're going. And that's a good point for me to the way that I put these exercises together to make sure that the, you know, the steps and the questions are clear what I want you to do.
Yeah, appreciate it. See you later.
All right, see you. Have a good
Thank you,
weekend.
Professor. Have a good one.
Bye-bye.